And welcome back. We are going to try to finish up Chapter 7 here. Last time we talked about the Poincaré-Bendixson Theorem, which is in some sense telling us how severely restricted the dynamics of an autonomous system can be in the plane. So we have shown when limit cycles have to exist, we have shown when they cannot exist. And what we'd like to be able to do is kind of blend the two of these results together, at least for planar systems. I mean, the eventual goal for dynamical systems in general is to determine long-term behavior in systems, in autonomous systems, in discrete maps. We would like to be able to know what happens eventually. And ideally, that would be with a minimal amount of analytic computation. So this is, in some sense, where we're going for this section, which hopefully I can make relatively brief compared to the past few videos. But in order for us to make sense or make rigorous the ideas that we are trying to employ here, we're trying to solidify, we need to beef up the abstraction a little bit. So I have to tell you a little bit about alpha and omega limit sets. So let's talk about this definition first. Right, so we would like to define for an arbitrary smooth system. Now remember, usually when we talk about manifolds, this is totally independent of the usual Rn definitions. So we've been working with systems on R, systems on R2, systems on a cylinder, and those, with the exception of the last one, those are usually working with states or solution states that are vectors, right? And typically when you use this vector notation, that means that you're dealing with a vector space. So manifolds are not necessarily vector spaces. So the whole reason why I'm dropping the vector notation in this system is for exactly that. We're trying to make sure that we're not restricting too greatly the types of systems that we're dealing with. So we're saying that we're dealing with an arbitrary dynamical system. And technically, I should say that this is done on at least a differential manifold. That way I have this idea of what a derivative looks like. And more to the point, I think it would be most easily studied if you work in the Riemannian sense, where you have a Riemannian metric at each point on the manifold, and you're dealing with, therefore, a Riemannian manifold. But for simplicity's sake, let's just say we have something that behaves like a smooth dynamical system on a manifold for right now. So we're going to define long-term behavior. We're going to define the eventual limits of what our solutions can do. So we're going to define something called the omega limit set. And this is omega of p pertaining to a point. And that point lives in the manifold. And this omega limit set is going to be the collection of all points in the manifold for which there is a sequence t sub n that approaches infinity with our solution x of tn approaching y along this discrete sequence, or at least along this sequence. So we're making sure that p comes into play down here by making sure that the solution that we are using uses p as its initial condition. Okay, so we're saying that we need to eventually get close to this point p, or this point y, in a limit if we start at p. Now, this is going to be a little bit weird to parse, a little bit tricky to digest. Like, why would I worry about a sequence instead of just the usual limit of the solution? Well, I'll show you in a moment. But first we got to make sure we also define the alpha limit set, which is defined very similarly. So we're still using p as the initial condition of the solution. And we are, instead of moving in forward time, we are going to take the sequence to go in backwards time toward minus infinity instead. So naturally, right, alpha and omega, they are the beginning and ending of these solutions, hence the names. So to make sense of what this definition is trying to get across, we should take a look at a quick example. And let's say that I'm dealing with something that looks like the following, where I have a saddle point at the origin, and I have an attractor on this, or that the red curve here is a stable limit cycle, and the point P in the middle is an unstable spiral. So what I'd like to show you is, based on this definition of alpha and omega limit, what exactly is happening. So for each of these points I've considered, right, I've got OX and OY, got A, and I've got B. So these 4 locations, I can determine the alpha and omega sets, right? So for O sub X, right, so X because it's sitting on the X-axis, I can go ahead and show you that if I move in backwards time, right, if I go against the grain, so to speak, of the vector field, that there is no limit here, right? I'm not going to be able to go toward anything. So there's never going to be any subsequence that approaches any point in the plane. It's all going to go off to infinity along the positive x-axis. As such, the alpha set, right, I'm going in backwards time, the alpha set is empty, right? On the other hand, if I start at OX and then move in the direction of the vector field, if I move in forward time, then the only thing that I can approach is this limit at the origin, right? Because I'm on the stable manifold of the saddle point, or so it would appear. So that would be this 0 limit. Okay? So very, very similarly, if I have an unstable manifold, if I put, say, OY on the unstable manifold, the alpha limit set now has an element in it, and it's the origin, right? I can move backwards in time and go toward the origin, no problem. Or if I go forward in time, then I'm going to have to push off to infinity, this time along the positive y-axis. So this is what's happening along stable and unstable manifolds. So top one would be a stable manifold, and the bottom one would be along an unstable manifold for a fixed point. Now, if I think about this in terms of these points A and B, so let's have a look at A first, right? If I want to know what points A can reach in backwards time, then I am going to follow the vector field backwards. I'm going to follow my solution backwards. And the only thing that approaches is the point P, because P was unstable, right? So in backwards time, it is stable. And it's the only point that the solution along A approaches in that direction. Therefore, my alpha set contains exactly 1 point, and it is that unstable spiral. On the other hand, if I move forward in time, notice what happens. I approach this entire solution. I approach this entire limit set. And that could be construed as a bit of a problem, especially if you're trying to say, oh, well, I want my solution to approach a limit. Well, limits are points as far as our usual construction goes. So what do you mean by the limit of a solution that wants to eventually oscillate? This is exactly what this sequence is doing. This sequence Tn approaching infinity is going to make sense of that. It's going to say, okay, you may not have a limit, but you have something that behaves like a limit. So if I make this the point that I want to get close to, this is the y in that definition for the omega set, then sure, eventually I'm going to have to get closer and closer to that point y as I go closer, or I go further and further in the trajectory along A, which means that there are locations in time that hit this at, say, T1, at T2, at T3, and so on. So that would mean that I have solutions that get close to each point of the limit cycle, but for different sequences in time. right? So it might happen every 2 pi units in time. It might happen every half a unit in time. But the point is that eventually each point on this graph or on this limit cycle can be realized as the limit of one of these x of t sequences. And that's why we need to have that piece in the definition. Therefore, if I move forward in time along the A solution, then yeah, every point along the limit cycle is going to be realized as one of those cycle steps, one of those x of t sub n sequences. And we can do this for the point B as well, right? B, it doesn't look like, if there's anything that B is doing, it might connect up with something else along this saddle trajectory, but then get slung off toward infinity along the positive x-axis. So the alpha set for B, we expect to be empty based on that picture. But in a very similar fashion, the omega set for B is going to be that same limit cycle. Right? So think about the alpha and omega limit sets as being the eventual behaviors of solutions, or solutions that pass through that point, or the solution that passes through that point. Now, that would mean that fixed points are omega limits and alpha limits, right? And limit cycles are these kinds of sets as well. And it turns out that there's a vastly more complex kind of behavior in higher dimensions that we need to acknowledge eventually. But the whole point of this section is to show the simplicity of what happens in low dimensions. So I'll tell you that the basin of attraction and repulsion can both be defined in terms of alpha and omega sets. I'll leave this as more of a definition for you to play with eventually, or play with on your own, but I'm going to leave this alone for the time being. And I never put this guy back. And now he's back. And now I'm happy. Okay. So, now that we have this idea of what alpha and omega limit sets are, we can actually restate the Poincaré-Bendixson theorem in the following way. I pulled this definition out of my copy of Wiggins from 2003. Right? If you want a reference, feel free to ask, but otherwise, I will leave it to you to find which reference I'm talking about. It's kind of his book is kind of a big deal, so I don't think it's going to be too hard for you to find. But we will say the Poincaré-Bendixson theorem, in an abstract sense, can be given as follows. So we're going to let M be a positively invariant region for the vector field containing a finite number of fixed points. And we're going to let some point be in that region and consider its omega limit set. Then exactly one of these things holds. Right? Either you're moving toward a fixed point. Great. So you're eventually going to be drawn in toward a single location. 2. The omega set of P is going to be a closed orbit, i.e. periodic, or some sort of, it's going to be some sort of nonlinear center, or part of a nonlinear center, or it's just going to be a limit cycle in general. And 3, your omega limit set consists of a finite number of fixed points, right? So you could go to any number of different fixed points, but your alpha set is going to also be on a fixed point as well. So we're looking at either going straight to a fixed point, closing up to a closed trajectory, or we're going to connect fixed points. And Poincaré-Bendixson says that this is the only thing that can happen if you have a trapping region. Right? That's this positively invariant region. So positive just means that it's moving in forward time. So just like we did in the last video, we're going to say once you enter this region, you cannot leave it. Right? But once you've established that, there's only a finite amount of behavior, a very, very predictable amount of behavior that can occur for that system. Right? The eventual behavior can only do one of effectively two things. go to a fixed point or close up into a limit, close up into a limit cycle or some closed orbit in general. Oh, wrong back button. There we go. So the theorem that we care about here, right, the thing that we care about in what this theorem says, is that none of these behaviors in the theorem statement constitutes what we're going to call chaotic dynamics. So in particular, the Poincaré-Bendixson theorem is powerful in the sense that smooth autonomous systems in no more than two state variables will never exhibit chaos. Right? So this seeming unpredictability or sensitive dependence on initial conditions, this cannot happen in low dimensions. Right? So chaos can only occur, intuitively speaking, if there is enough room to avoid the planar trapping regions that we get from the Poincaré-Bendixson theorem. Right? So if there is any way for us to kind of reduce the dynamics to a two-dimensional manifold and then trap it, then there's really only so much that can happen in that omega limit set. Okay? And this is the whole idea, the whole importance behind Poincaré-Bendixson is that we are limiting the kinds of dynamics that we can see in this dimension. Now, there's a generalization to this result, and I think it's worth mentioning because there's only a handful of textbooks or references that really do mention it. But it's, I think, really important to know exactly how you can classify dynamics in certain dimensions so that you know how much complexity your model needs to take into account if you see certain behavior in your physical phenomenon. So whatever you're trying to model, you need to be in the appropriate setting in order to show the mechanism or to show a mechanism that could create it. So for dynamics on an arbitrarily closed and bounded surface, so a compact two-manifold, and we're going to go ahead for the sake of simplicity, say it's connected, a Brazilian mathematician by the name of Peixoto was able to classify all the generic behaviors that one could expect on that manifold. So just like in the plane, we can totally understand the omega limit sets of solutions that enter trapping regions. We can do the same thing for an arbitrary compact two-manifold. Right? So this is the idea behind structural stability as well. You want to be able to say what kinds of behaviors are immune to small perturbations of the vector field, and in this case, it'd be that little F vector field right there. Okay. So, oh, shoot, put that back and then go back here and there we go. I'm back. So the theorem that I pulled is, I didn't put it in here, but this is from Perko, and I forget what the date was for Perko. I think it's sometime in the 70s. Yeah, that sounds about right. Perko 70s? Question mark. I'll look that up later and amend the notes if I have to. But the point is that F is, in some sense, only immune to these small perturbations and gives you the same dynamics under those perturbations if there's only a finite number of hyperbolic critical points and limit cycles. So you can't have an infinite number of either of these. I think that would imply that you would have a non-isolated critical point or limit cycle eventually, because we're on a compact manifold. Number two, there are no saddle connections. Right? Saddle connections can actually be broken very easily, and I have a homework problem for you designed to show you exactly that. So saddle connection, I'm saying that we have two saddle points here. They're connected in this way. That would have to be unstable, which means this guy is stable and unstable. There we go. These saddle connections can actually be broken very, very easily. So specifically, I have my saddle connection. It can go like so. Yep, there we go. I do remember how to draw these. There we go. Happy trees. There we go. But these saddle connections are not immune to small bumps in the vector field, small perturbations, right? So those connections are not stable. They won't stick around if you kind of perturb the vector field slightly. And there's this idea of the non-wandering set. So these are kind of combinations of alpha and omega limit sets. They're telling you what eventual behaviors you can have in your systems can look like, what your eventual invariant sets look like. And these non-wandering sets can only consist of critical points and limit cycles. And in effect, that's Poincaré-Bendixson. Right, so Peixoto showed the Poincaré-Bendixson theorem on arbitrary compact 2 manifolds. And specifically, if this guy is orientable, then structurally stable vector fields are an open, dense subset. And that is particularly powerful, I must say. And you know what? I'm going to quit talking about it because I think this is going to be somebody's project. I think this would be a great, great opportunity for someone to explain what this is doing or what this says about the dynamics for low-dimensional systems. Right? Again, there is no chaos in this setting, which is a huge deal. Right? Chaos is something that we either want to induce or avoid, but in either case, be able to predict when it's going to happen. Now, Poincaré-Bendixson and Peixoto both show that chaos is impossible in this setting. And more to the point, we're looking at this idea of structural stability. And this, as it turns out, is different from being generic. Right? Like a randomly chosen system need not be structurally stable in high enough dimensions, but that's a very deep result, far beyond the scope of our class. But what I wanted to make sure we understood is that there is this idea that chaos does not occur in low dimensions. So we're going to have to move up in dimension if we're going to see chaos. And we might move into that, or we are definitely moving into that very soon. But until then, there's one last thing I wanted to talk about for chapter 7. It's technically one chapter ahead of where Strogatz talks about it, but I want to talk about it here because I think it makes more sense to talk about it at the end of chapter 7 than it does to talk about it at the end of chapter 8. So let's go ahead and talk about that.